Hello, and welcome to Predicate Logic. My name is Dr. Angela Siegel, and let's just dig right in. So we've already covered propositional logic, and propositional logic we used to encode Boolean expressions. Now we'd like to move on to predicate logic, and predicate logic is just a more general type of logic. It can be used to express a broader range of notions. And what does that look like? What does this word predicate even mean? So a predicate is many things. A predicate is a function-like expression. Unlike Boolean expression, they are not true or false. So these are values that are not true or false. And it's a property. So it's a property that a particular entity might or might not have. When we looked at propositional logic, we looked at things that had a quality or did not have a quality, but this is more of a general expression where we talk about the property of possibly having a specific characteristic. So when we looked at propositions, these were those Boolean expressions that had true or false values, like our example, lowercase p, the number 24 is even. A predicate is a bit more general. And it talks about the concept of a number being even. So the number blank is even. And in this case, we use the variable x to represent some arbitrary number. And so a predicate p of x could be defined in terms of x, where x is undefined. The number x is even. Let's look at some examples of predicates and propositions. So predicates are like propositions with blanks in them, details that need to be completed. So for instance, the predicate, the integer blank is prime, talks about the property of a number being prime. It's a particular number has the property of being prime or not being prime. But as a statement, a predicate doesn't have a truth value. It's not true or false on its own. Whereas a proposition is stated with that blank filled in. So the integer 17 is prime, and that is either true or false. And in this case, we know it's true. Another predicate is the student blank is in a specific class. If we fill in that name, we could then check that the student is or is not in the given class. The string starts with an A. If we have a specific string in mind, we can have a truth value. The string apple starts with an A. The string banana does not start with an A. And so if we inserted banana into the predicate on the left, this would be a false proposition. But at the moment, we've not specified, and so we don't have a truth value associated with predicates. The integer blank evenly divides the integer blank, so we can have predicates that require more than one variable, x and y. And we can have propositions that are built up requiring more than one integer. The string A comes alphabetically before string B. As a proposition, these would be filled in. The string discrete comes alphabetically before the string mathematics, where on the left, these are arbitrary values that have not yet been populated. Propositions are about specific entities, specific objects. A predicate is a Boolean valued function. What that means is we start from some universe of interest, our domain of discourse, and that universe is then mapped to the Boolean values true or false. We say that this function p, the predicate p, is a predicate over u. And so then if we put together a set of all the objects within the universe that meet this criteria, so all objects for which p is true, is defined by the set x and u such that p of x holds. And p of x is either true or false, and so that is a proper definition of a set, and it's a set of all the objects for which p is true. So let's take a look at an example of some predicates, and we'll see that we've given them names that are meaningful. So the first is prime. which states that the positive integer n is a prime number. And so it goes over all the positive integers and it maps it to the Boolean value true or false. And so we know that prime numbers are all those numbers greater than 1 that are only divisible by 1 and itself. And so we know that if we took 2, 2 is going to return true, 3 is going to return true, and 4 is going to map to false, because 4 is a composite number. It is not prime. We could have a predicate sum of two primes, and sum of two primes states that a positive integer n is equal to the sum of two prime numbers. We could look at the predicate is power of 2, and this states the positive integer n is a power of 2, so it's equal to some power of 2. N is equal to 2 to the I for some non-negative integer I. And we could expand upon that and say, are all powers of 2. And instead of taking in an integer, this time we'll take in a set of integers. Every element in the set is a power of 2. And so we can make use of existing predicates in order to define that. And then we can use this even further, and we can go beyond sets. We can look at a position within a game board, for instance, a chessboard position. But we needn't limit ourselves to integers or sets. We can go even further, and we can take in information to store a chessboard position, where the pieces are, and we can instead state that this predicate is that the chessboard position, B, can be won by the next player. And then we can use that to decide who should win the game. So let's look at a few examples. The first is the first predicate we discussed, which is prime, which states that the positive integer n is a prime number. And we said that this is a function, and it goes from all the positive integers to the Boolean values true and false. So propositions from this predicate can include things like, is prime 16? Or is prime 17? Is prime 16 states that the positive integer 16 is a prime number. And is prime 17 is a proposition, the positive integer 17 is a prime number. And so what are the truth values of these propositions? This is whether or not is prime 16 is true or false, whether or not is prime 17 is true or false. And so we know that is prime 16 is false because 16 is equal to 2 times 8, which means it's a composite number, and so it's not prime. Is prime 17 is true, and you can check that there are no numbers less than 17, other than 1, that divide it. Our second example is the sum of two primes. So this states that a positive integer n is equal to the sum of two prime numbers. And this is a function going from the positive integers to the Boolean values true and false. And so propositions of this predicate could be of the form sum of two primes of 5 or sum of two primes of 17. And we could check if we want to identify the truth values of these two propositions. We can see that 5 is equal to 2 plus 3. 2 and 3 we know are prime numbers, so this meets our criteria. So we believe that this will be true. And to check 17, we need to remind ourselves that for any numbers, the only way to add to an odd number is to be odd plus even, because even plus even is even, and odd plus odd is even. And so because there's only one prime number that's even, which is 2, if this is going to work to be true, we'd have to have 17 is 2 plus some odd prime. But we know that for that to work, it would have to be 15. And so the problem is 15 is not a prime number. And so there are no two primes that we can add together to get 17. So the truth values for these propositions, the sum of two primes of 5 is true because 5 is equal to 2 plus 3. The sum of 2 primes of 17 is false, and that's because there's no even prime number greater than 2. Our final example is the predicate function all are powers of 2, which states that every element in the set S is a power of 2. This will be a function. We're defining this to be a function that takes a set of integers, positive integers, and it maps them to the Boolean values true, false. And so a proposition that we can form from this predicate would be of the form are all powers of 2, and we're going to take in the set 1, 16, 128. And the truth value of this proposition, well, we can check quickly that 1 is equal to 2 to the 0, 16 is equal to 2 to the 4th, and 128 is equal to 2 to the 7th. So are all powers of 2 is true because of that fact.